Well, hello and welcome everybody. We're glad you're here. Enjoy. This is a discussion about a suggestion for the program called Sketchup. As you watch this, it's about a tool that I would like for Sketchup to include in Sketchup. My thought would be watch the video. If you like what you're seeing, then you should send a message to Sketchup that you saw Dr. Gray, that's me, Dr. Gray. You saw Dr. Gray's video about a new tool for Sketchup, and you think it's a good idea, and you think Sketchup should have that tool. I don't know how else to do it other than to make that suggestion like that. Anyway, this is a picture of a robot that I created. It's a creation inside Sketchup. It doesn't exist as a real item because it's too expensive for me to create it, but there it is. And this tool I'm talking about is related to Sketchup projects like this. Now, this picture here is actually a picture from a rendering, and that rendering was in a program named Keyshot that rendered the robot. And you can see that using some video trickery, I took the Keyshot grass or scatter. It's an extension in Keyshot called Scatter that allows you to create this grass. And I put the robot on the grass, and then I put a picture of the trees behind it. And then if you tighten up the viewing with the camera, you can do a rendering where you have the robot, and he sort of looks like, or he or she looks like he's or she is standing out there in the forest, and that's all that is. So now we can go and take a look at the robot in in SketchUp. And that's that same picture that I simply, this is my SketchUp Pro 2021, okay? And that's that image that I just imported into SketchUp. And over here is the same real robot just standing on a little floor that I made. And the point of this robot, I wanted to make a robot that moves and looks and has the proportions of a human being. It's confusing to me that nobody has done that. It's just weird. And I thought that pistons are a much closer approximation of human muscle action than is rotary encoders. And one advantage of a piston is they have that linear motion like muscles do. The other advantage is you can put a tremendous amount of force and energy into a piston, mostly because the equipment that's generating the hydraulic fluid to pressurize the piston is somewhere else. So in order to get a lot of strength in this thigh muscle, you can see that that's a thigh muscle for the robot. In order to get a lot of strength in this thigh muscle, you don't have to put a giant motor down here. You can have the motor and the pump and all that other stuff somewhere else. And so I thought it would be nice if I could show this robot moving around, and that is actually kind of hard to do in SketchUp because of the way that SketchUp is structured. And so I thought, well, let's see if we can make a tool in SketchUp that works like the tool called rigging. That's the name of it. It's called rigging. It's in the AutoDesk group of programs like Maya. And rigging is something that Autodesk makes available for people who are creating cartoon or at least fake characters that they want to have them move around so they can make cartoon movies like Pixar and all that stuff. And they wanted to make those models where they could move around easily so people would not have to work so hard. And I don't know why we can't have rigging in SketchUp. I do think, and I understand, that the total capability of rigging that's in Autodesk Maya is probably too expensive for SketchUp to offer. And so this tool that I'm talking about is like the poor man's rigging that works inside of SketchUp. We'll see. And this is more of our tools discussion. I wanted it to be a tool like tools here, like push-pull or protractor. I was going to name it articulations. I guess we could name it joints, but you know, the word joints has some negative connotations, so I was going to leave it out and call it articulations. I should mention I had the robot in KeyShot standing on the grass. The grass extension, the way I created that was a SketchUp extension called Scatter. I created it, and then KeyShot can import that image. I said it was a KeyShot extension. It's not a KeyShot extension. It's a SketchUp extension. And you might be saying, well, why are we talking about a tool in SketchUp and going over this robot stuff? And the only point I'm making is, I thought perhaps if I showed you an actual example, it might be clearer what's going on. And so here's the little robot, and the thing about walking, now remember that a human being is a balanced bipedal walking device or thing. And it's very important to understand that the process of walking includes that you have to take a leg, like the right leg, and you have to get the right leg from where it is right here and move it forward. And right now, if you look at this robot is balanced. Half of the weight of the robot is on the left leg and half of the weight of the robot is on the right leg. So the robot is not going to be able to do anything with its right leg because it's holding up half of the robot. And in order for this to work, you have to have joints that can articulate and move around to allow walking. And to show this more clearly, I have another view that I'll show you. And this is another SketchUp drawing where here is this robot standing balanced with his or her weight evenly divided between the two legs. I was working on demonstrating a deep knee bend to show forces related to this muscle. But this deep knee bend does demonstrate another thing, which is that this robot has no weight whatsoever on this leg. This left leg of the robot is up in the air. And the way that the robot went from this to this is the robot took the weight of the robot. Let's see, if we take a straight line, okay, and you can see that the weight of the robot is pretty much balanced in the middle of the robot. That's what this is showing here, okay? If you take that same line and put it over here and let it be about where the weight of the robot is, just using your eyes, about half of the robot is over here on this side of the line and the other half of the robot is on this side of the line. So the robot has all of its weight over its right foot and right leg. And this is the process that allows walking, because as the robot or human unweights or takes the weight off of one leg, that leg becomes a free leg that can be picked up and moved forward. So if this robot was walking, now that he's got his left leg off the ground, he can take his left leg and move it forward and put it down. And in order to do that, you can see that this lower leg on the right is directly over the foot. And the knee is pretty much almost over the toe. Over here, you can see that the knee has moved laterally away from the foot. The knee is no longer over the foot. And in addition, there's a little bit of more motion of the knee forward. So the lower leg of the robot has moved with respect to the foot. Not only has the lower leg moved this way, but it has also moved this way with respect to the foot. And this is the motion that we're trying to capture, and we're trying to see if we can work out a way to do this with rigging where it's not so hard to do it. All right, and we're getting deeper and deeper into the details of the robot, but it's important, as you can see, all right, right here, the foot touching the ground. All right, the rest of the robot is out in the air, bothering nobody, interfering with nobody, starting no trouble. Underneath the robot is the planet Earth, also interacting with nobody, bothering nobody, having nothing to do with the robot. Right here at this point, at the foot of the robot is the place where the robot and the planet Earth become acquainted with each other. And I'm not real sure how much this robot would weigh. I made it to be the same size as a human being. I made it to be designed out of aircraft alloy aluminum. I really wanted it to be a military type robot. So it may weigh at least as much as a human being. And the rubber meets the road, the place where the robot and all of the weight of the robot and the shock load of the robot and the interactions of the robot with reality are all going to occur right here at the foot of the robot, the lower leg, ankle, and foot of the robot, where these structures run into the ground. And the reason we mention that is, you know, you can design anything you want to, but this may not be the place where you want a frizzy, delicate, multiple tiny little parts that all interact together, and you know they're the size of a postage stamp, because this is the place where everything related to this robot slams down into the ground. So what I'm trying to say is these parts need to be robust, big, and strong. And parts built in that way, it's very easy to design stuff if you don't care how big the parts are. But if you want the parts to have enough strength that they really can walk along, I want this robot to walk all day long, which means this foot is going to be picked up and put down thousands and thousands of times. So all of these structures need to be big enough and strong enough to withstand that kind of work. And so what happens with structures, as they get bigger, they begin to bump into each other. And so you can't have the articulation that allows the foot to go back and forth this way. That articulation cannot be sitting directly on top of the articulation that allows the foot to go back and forth this way, because those two articulations are separate axes of motion of the foot. They're both important, and they both have to be strong enough that they can withstand the pounding of the robot as it picks his feet up and puts it down on the ground. And so some complexity begins to occur when you bring reality into the issue of your design. And just some design points. It's clear to me because I created it, but there's clearly going to be a shaft here that keeps all these parts from going anywhere. And there's going to be a shaft here that goes through there. Some of the shafts, like I put a shaft in here, but some of these places I did not put a shaft in to show the connection with a shaft, because it makes the drawing start to get so complicated, you wind up not being able to see anything. And and the other thing we want to show was the foot. You can see that the foot has basically, this would be the right foot, so it has a right great toe, a right little toe, and a right heel, and they all have their own internally constructed parallelogram type structure to allow the toes and the heel to be independently moved. All this is done to try to give the robot the ability to behave like a human being, again, with construction techniques where everything is big enough and thick enough that it's not going to get broken. I do have these little drawing points here throughout because when you're rotating these structures, you want them to rotate around the proper axis, and this helps to locate where that axis is. It's floating out in space here, and that's just to help to line it all up. Like here is this bearing has to be in between these two bearings, and so here is the little triangular drawing that shows where this bearing is, and so you can sort of line these all up and show that this is pretty much lined up, and that's all that is when you see that. The final thing is this is a fairly complicated structure, and it can chew up the ability of your computer to do much of anything. So I'm going to simplify it down to a smaller size. Okay, and more detail. This is a much simpler drawing. Now, to me, it's easier to visualize stuff if you take these structures that you're worried about and put them on something. And so that's why this lower leg is sitting on this. Now, in order for people to walk, they basically sway their hips back and forth. In order to get the weight off your left leg, you have to sway your hips off to the right. And that gets the weight off your left leg, and you move your left leg forward and put it down, and then you sway your hips back to the left. Because as you sway your hips back to the left, it takes the weight off of your right leg, and now you can pick up your right leg and move it forward. And the extent to which you sway your hips back and forth is related to how far apart your feet are on the ground. And what this means is you're better off, if you can, to have the width of your foot and ankle and lower leg not to be very wide, because then the two, the right foot and the left foot, can be close together. And if the closer they are to the midline, the less of this swaying stuff that you have to do. And the importance of that is to bring out what we call the long axis of the leg. And we would like the pistons that are running the leg to be aligned in the long axis of the leg. And so we want these two pistons to be sitting right next to each other so they don't run into each other as the right foot is still and the left foot swings by. You don't want parts of the left foot to run into the right foot and vice versa. So these are all design considerations. But what that means is the pistons running the behavior of the foot need to be aligned, the long axis of those pistons, and technically this blue thing is the piston. That's the arm of the piston, that's the head of the piston. This entire structure is a hydraulic cylinder, but nobody calls it that, so I'm calling them pistons. So the long axis of this piston needs to be aligned to the long axis of the lower leg, and the long axis of this piston needs to be aligned to the long axis of the lower leg. And we have two separate motions of the foot with respect to the lower leg, and those motions are the place where we call the ankle. And we should be able to click down and select all right, this is just the foot. Now, according to Sketchup, you can invert the selection, which never works. So, it has to do with the nature of Sketchup. But anyway, all right, the motion of the foot where the heel goes up and the front of the foot goes down is called flexion. These phrases come from medicine, and it's not worth bringing out or creating brand new phrases. So we just use those. And if you move the toes down and the heel up, that is called plantar flexion. And if you move the heel down and the toes up, that is called dorsiflexion. And one of the movements of the foot that we have to have is dorsiflexion and plantar flexion. And to show the motion of the foot up and down, we might be able to get this rotation to work. Okay, you can see that this is aligned with green. So we can hold down the green and force this to be green, or force this to be the axis of green. And so we can take this foot and tilt it. There you go. That is plantar flexion, and that is dorsiflexion. And it's important to understand that actually the ground doesn't move. So the foot, when it dorsiflex and plantar flexes, it isn't the foot that moves around. It's the entire robot on top of the foot that moves around. It's just you can't quite do that easily in SketchUp. So we're moving the foot back and forth, but what would really happen if we wanted to do it is you would have to move, you know, you'd have to, let's see, I'll pick a number. I'll move it down by 3 degrees. Okay, so I moved it by 3 degrees. I'll type a 3 over there, 3. Then you have to come out of this entire structure and choose the whole structure. Go back to this same rotation point. And move everything back by 3 degrees. So now the feet are back settled on the ground, and you can't see it because it was only 3 degrees. But what we did is we moved this lower leg that way a little bit. Okay. So this is the dorsiflexion and plantar flexion. The other motion of the foot that we need to consider is inversion and eversion. And inversion of the foot, let's see now, we'll have to select that. So that might be it there. Okay, so that's not selected. So it's the only thing we've selected here is the foot. See that? And so we can dive in here and put our rotation device on this axis. That's why these marks are here like this. And then come back out and take a look at the foot moving around. So when you take the foot, when you take the big toe down towards the ground, that is considered inversion of the foot. When you take the big toe and lift it up, that is called eversion of the foot. And the reason why we have to talk about inversion and eversion is because as you move the knee over, remember, we're taking the weight of the robot and we're moving the weight of the robot so that all of the weight of the robot is over the right foot. And that took this part of the knee and moved it that way. And so what we did was we inverted the foot. But remember, the foot is on the ground. And so when you invert the foot and the foot is on the ground, what happens is the entire rest of the robot moves over. Complex, but it needs to be understood. And I think you're beginning to see that it sure would be nice if we could do something where all of these different motions that have to happen could all happen in a way where they're forced to behave themselves and correlate together instead of us trying to remember how to do all this. And so now we'll look at a little more detail about the two motions of the foot that we're talking about. Dorsiflexion and plantar flexion. The axis of rotation As a matter of fact, when I was showing this to you just a little while ago, I picked the wrong place to demonstrate how the foot moves in dorsiflexion and plantar flexion. So this plate here is the plate that allows controls dorsiflexion and plantar flexion. And these connections here are the connections that allow eversion and inversion. And the actual place, as you can see, here would be the knee, and here is the ankle. So the place where the foot rotates when it's doing dorsiflexion and plantar flexion is actually right here. That's dorsiflexion and plantar flexion. And the way that dorsiflexion and plantar flexion occur is because this piston here moves up and down. So when that piston moves up and down, the effect that it has is it pulls up and down on this plate, and this plate rotates this way around this axis, and this plate is connected to the plate that is the foot. So, and the axis of rotation, now you can see in this drawing that we're demonstrating this robot to have moved itself so that it's got all of its weight centered over its right foot, and so the knee is shifted laterally. So that the axis of rotation of this foot with respect to dorsiflexion and plantar flexion, that axis of rotation is this axis. You would think, since the foot is flat on the ground, that it would be well, normally I can grab a line of a demonstration line, but it doesn't want to let me do it. Okay, so this line here is a completely horizontal line, and you would think that the axis of rotation for dorsiflexion and plantar flexion would be this horizontal line here. But since the leg itself has been tilted over this way, the true axis of rotation for this specific example, and again, I don't have any way to force this. I would have to go all the way back out here. All right, we'll start again. So here's the red axis here. So this leg is tilted off to the right because the robot is trying to keep itself in a position where all of the weight of the robot is over the right foot. So the actual center of rotation, or the actual place of location of the rotation axis, is an axis that looks like that. It's not a big deal. I'm just showing you that this gets remarkably complicated, and it is difficult to properly line everything up if you have to keep up with all of this. It's the only point I'm trying to make here. But that is the axis of rotation for dorsiflexion and plantar flexion. And the axis of rotation for eversion and inversion is the axis that goes from this rotation point to that rotation point. And if you want to look at inversion and eversion, then instead of the portion of the foot that includes this this bluish square here, this is the square that was used to cause or create dorsiflexion and plantar flexion. What we want for dorsiflexion and plantar flexion is to be all the way down where the only thing that's moving is this lower area of the foot rotating around these shafts. And the axis of rotation for eversion and inversion is an axis that looks like this. Okay. Now, the problem that you get into from a programming viewpoint is it would be nice if you can structure the programming where if you wanted to have inversion or eversion, you could ask for that. And if it happened, it wouldn't alter the value for dorsiflexion and plantar flexion, and vice versa. And that's the other point we're going to show here. And from a programming viewpoint, the programmers are going to appreciate if when they send a control in to make, for example, to this piston, to make dorsiflexion or plantar flexion occur, they are not going to have to send in a compensatory programming instruction to this piston. If this this is the piston that causes inversion and eversion. If this was simply anchored to this leg, then when this piston caused dorsiflexion and plantar flexion, because it's moving this plate around, it would also create eversion and inversion. And you would have to have a program adjusted so that whatever you did with dorsiflexion and plantar flexion, whatever that dorsiflexion, plantar flexion command did to inversion and eversion, the inversion and eversion piston would have to receive a set of commands to undo that, which is complex. And it could be that you can get out to where you're outside of the range of what this piston can do. And it occurred to me that there is a way to get that problem to be almost absent and much less. And the way that's done is to take the anchor point of the inversion eversion piston and move it out to a swing arm. So here is the inversion eversion piston. Here is the anchor point of it. And that anchor point has been sent out to this swing arm. And this, once again, same deal. There would be a shaft that goes through here. And I don't have these totally lined up because it's difficult. It's not impossible. It just takes time. But these would all remain completely lined up all the time because they would have a shaft in there. So there's no way that they could be anything other than lined up. And so the top of this inversion eversion piston is not anchored to the leg. It's anchored to this swing arm. And the interesting thing about this swing arm is that this swing arm is connected by another connecting rod to the shaft that is the pull point or the push point for dorsiflexion and plantar flexion. And so what happens is when you send a command to the dorsiflexion, plantar flexion piston, and it lifts up on this plate to cause dorsiflexion or plantar flexion. When it moves this plate around, it also moves this linkage arm. And this linkage arm also moves the anchor point of the eversion and inversion piston, so that the relationship of the eversion inversion piston to the foot is maintained even though you change the value for dorsiflexion and plantar flexion. So eversion and inversion should not change very much just because you did dorsiflexion and plantar flexion. And the independence of the eversion and inversion piston, anyway, it was always independent, means if you change eversion and inversion, it's simply rotating around this shaft here. The changing of eversion and inversion isn't going to have any effect on dorsiflexion and plantar flexion. And now, because of this linkage, where we're indexing the anchor point of the eversion and inversion piston, the anchor point of the eversion inversion piston has been indexed to the piston that controls dorsiflexion and plantar flexion. And because of that, whenever you send in commands for dorsiflexion and plantar flexion, yes, they do, in fact, change the value of dorsiflexion and plantar flexion. But since the eversion inversion piston has been indexed by this linkage, the value of eversion and inversion does not change, even though dorsiflexion and plantar flexion did change. And again, you might say, wow, if there's any way you could make this more complicated, it would be fun to see it. Sort of like, why? What is the point? But that goes back to our design criteria. We want this lower leg to be narrow so the 2 feet can go beside each other, so that the swaying back and forth when you walk is minimized. It's a more efficient walk. In addition, you can see, if you'll look at all of these structures, they're very big. I mean, let's just look at, let's take this to inches. So that's 3/4 of an inch. And the diameter of this shaft here is, I mean, this is 1 inch. So this is 3/4 of an inch. And of interest, if it's alloy aluminum, then which has a tensile strength. And here we've pulled up one of the alloy aluminums. Here's the tensile strength, 165.5 megapoise atmospheres. And we can go look at that with our other calculator program that does conversions. So this is millipoise atmospheres to pounds per square inch. And let's put a 165 in there. So this is 23,000 or 24,000 pounds per square inch of force that this can withstand. And if that's a 3/4 inch shaft, then the radius is 3/8 inch. Okay, so the surface area of it is 0.44 inches times 10,000. So the compression strength of this shaft is 10,000 pounds. So what we've created here is a foot that can take a substantial amount of force and won't bend, distort, break, or quit functioning. And so the final point that we make here is we are now, if you wanted to change this foot around, you would have to individually in Sketchup go into each one of these parts and move them around. So if you shortened this piston stroke and changed your dorsiflexion and plantar flexion, then you'd have to move this connecting arm, and that moving that connecting arm would alter this swing arm. And if it altered that swing arm, you'd have to lift this whole piston up and reconnect everything. And all of those movements are precise and delicate and important, and it's just a lot of work. And so we wanted to see if we could make an articulation program where you can link all these together and the movement of them happens for you, and you don't have to do it individually each time. And of course, one way to solve the problem of doing these drawing changes is the brute force method of just doing it in SketchUp. It takes a long time. You can see here I have a robot standing there on his right foot getting ready to start walking, and I divided walking into 22 steps. So he's on his right foot, and here he is on his right foot getting ready to swing his left foot forward. So if you look at this stance, the next position the robot would be in at the end of this stance would be in this position. And you can see that the robots are tilted off to the right, so they're trying to put their weight over their right foot. And when they lift it off, when they've tilted themselves off to the right, it unweights their left leg so they can lift up their left leg because there's no weight on their left leg. And then they start leaning themselves forward, and that shifts their weight from being over their right foot to being, it's beginning to be where their weight is over their left foot. Notice that he's almost ready to lift his right foot off the ground. And of course, in order for him to lift his right foot off the ground, he's going to have to start tilting himself or herself to the left to get his or her weight over the left leg, because the only way to get the right leg off the ground is if the right leg is not holding any of the weight. And I don't know if you can see it. But it has a kind of a, see, they're tilted off to the right, and now they're sort of tilting off to the left, and now they're tilting off to the right, and now they're okay, so that is that swaying back and forth of the hips. And all of that activity is being born with this foot, the anchor foot, staying flat on the ground by changing the values for all of these different parts, which I did one by one, a tiny bit at a time. It's okay. I mean, you just have to decide whether you want to do that kind of work or not. But it would be nice if there was an articulation where all of these joints were forced to be the way they're supposed to be, so that if you, for example, as would happen in a physically real structure, if there was a shaft right here and you lifted this up, it would lift that up. And if you lifted that up, it would lift that up. And if you lifted that up, it would lift that up. So it would all work together. And that is an articulation. And the next step that we want to work through here is the design for an articulation program for SketchUp. And I understand that a fully functional, perfection level articulation system, rigging, as you see in the AutoDesk programs, is probably too expensive for something that SketchUp would want to offer. So I'm going to try to show an articulation program for Sketchup that I hope is inexpensive enough that Sketchup could offer it. I don't have the programming skills to actually create the lines of code that would do the articulation tool. I just would like to show how to make it look so that I think people could use it and would be happy with it. And that's what we're talking about. All right, and we'll spend just a moment to look one more time. This is an articulation program. That is the equivalent of saying that this physical structure, this piston, or actually this piston rod, actually very specifically, this bearing end of this piston rod has an articulation with the bearings on this blue plate. And they have an articulation with this traveling arm or movement arm or indexing arm. And the articulation is because of a shaft that goes right through here. Basically, whatever this piston bearing end does, whatever it does, this does. And whatever constraints there are on the motion of this bearing on the blue block, those constraints are transferred to being constraints on this bearing end of the piston rod. Because surprisingly, this piston rod is this distance from that rotation point, that distance right there. But as this piston rod goes up and this rotates, the distance of this piston bearing from the end of the leg changes. It gets closer to it. So not only does this piston shaft move up, but the whole entire piston structure has to rotate in just a little bit, not much, but it has to. And what you want with your articulation program is a way to force those things to behave themselves and link together. And, to me, this is pretty. I think it's just absolutely cool. It's hard for me to know, is it pretty because I created it, or is it just pretty? But I think it's kind of cool. It is complex, though. And I think we can talk about articulation using a simplified concept. And I've spent all of this time showing you this leg and ankle to give you an appreciation of how nice it would be if you could have an articulation program so you don't have to program all these steps. But we're now going to go over to the more simplified format. And so here we go with the articulation suggestion. I'm going to just talk about it like it exists, understanding that it's a suggestion. I do completely understand that Sketchup would have to look at it and they may decide they don't want to do it, or they may decide that I've made a math error and you can't get it to work, or they may decide that they want to do some parts of this and they don't want to do other parts of it. All of that's okay with me. I would again suggest, as you watch this, if you're interested and would like to have this, send a note to SketchUp and say, yes, I saw Dr. Gray's articulation suggestion and it's cool. I would like it. Now, here we go. As is true of human life, you're in college, you're a junior or senior, you take some time off, you're in Venice out there on the plaza. It's morning, you've got your sweet bread and some coffee, and you're just looking there at what's around you and the people and how pretty it is, and there's another person right across the table next to you, and you start talking to that person. That person seems interested in you, and you find that you're interested in that person, and you talk some more, and you walk around some more, and you become friends. It turns out you're both Americans. You go back to America and you stay together and you talk, and pretty soon you're a couple and things have happened, and off it goes. And as is true of this program, which started out with these little things, it turned into the discussion of articulations and what is necessary and the parts. And all of a sudden, as is true with those two people, suddenly all this time has gone by. It went from this to all of that, and you have grandchildren who are requesting if it'd be all right for them to take your car to college, the old one. You don't drive that much because they'd like a car and they're not wealthy enough to buy one. So you start out with an articulation program, but when you put into it everything that it needs to have, it just starts to look like this. And I don't want that to trouble you or bother you, because I think a lot of the way in which an articulation program can help you is if you get control of all of the variables. And if you don't have control of all the variables, you're not going to be able to get this to do what you want it to do. So, and remember, as is true of a lot of these things, you get out into these branching decision trees. Once you've made all your decisions, sometimes you can stay over here in the simple part, just the simple part. All right. All right, and so we're working to set up a controller that will make the parts of a SketchUp drawing move in a certain way. And it will be based on a concept of restrictive permission, which is that in normal SketchUp, if you select a group and get the rotation tool or the move tool, you can rotate it any way you want to, on any axis that you want to. And you can move it any way you want to. You can move it on the blue axis, the green axis, the red axis. This is going to be a system of restriction where, while there are thousands and thousands and thousands of different movements you can do, you're not going to be given permission to do any of these movements because you are using this articulation tool. So when you put the articulation tool in place and use it, it adds restrictions to how you can move around groups in SketchUp. And if you don't want those restrictions, you can just turn off the tool. I suppose we probably should have a line in there where you can click something where the articulation tool just isn't working. But that's how this works. And if you want to have SketchUp working like it always works, then don't add the articulation tool. Now, I explained things to people for a long time, many years, where it was very important that they understood what I was talking about. So I explain stuff slowly. I try not to, but sometimes I will simply repeat what I said a slightly different way. And it's just a habit that I have from trying to be sure when I explain things that people understand it. And all of this, at any point, if we're talking about something that you already know about, then just skip it. And it does show some of the things that happen with moving stuff around in SketchUp. So if you're new to SketchUp, you might want to listen to it just to see concepts about moving stuff around in SketchUp. And basically, I'm going to let it run in a way where there's a tool and you can do a tool like this. It will drop down and it will have articulations. And when you click on articulation, it will come to this. And when you click, if you put the arrow in there, nothing will happen now because it's not a functioning program. But if you put your arrow in here and clicked it, then you would go to the main menu. And if you put your arrow in here and clicked it, you would go to the show pop-up, or the show pop-up, the pop-up of articulations would pop up. So that's how this works. And it is a sequence of embedded screens where one screen leads you to the next screen. And when you get to show, so that's what I'm going to do, is go through them. Now, I suppose I should show one thing here. So we are back into this ankle joint where the knee is shifted in front of the foot, and the knee is also shifted off to the right of the foot. This is the right foot. And we have some of these controllers that I've put in here to show how this would work. And one thing I think I should mention, you can surely see if this robot was walking around in the forest or the dirt and got a rock or a piece of wood or a twig or mud in there, it's going to mess up how all this works. But human joints are the exact same way. If you put a grain of sand in a human joint, they probably wouldn't be able to move because it would hurt so much. So I think if this robot was ever constructed, that you probably are going to need to put around it the same type of material that they use to make a scuba diving suit, the closed cell neoprene foam that would be around all of this and zipped shut. That foam is flexible enough to let all this motion happen, but it would keep out rocks and stones and twigs and mud and dirt. And I suppose if you had a robot that was walking around, you could probably make a leather boot for this robot and let this foot and ankle and some of the lower leg would be in there inside of their scuba foam suit, and then that whole thing would be put inside of the leather boot. I don't know why that couldn't happen, but it was just something I thought I should mention. Here is some of the controllers. You'll see that I've made them different colors. It's going to become important as you work with this to try to remember what controller are you working with. So that's why I gave them different colors. And we decided that we would just pick something. So this plate right here, this blue plate, is the plate that controls dorsiflexion and plantar flexion of the foot because of the motion of this piston. The pivot point for dorsiflexion and plantar flexion is here. The piston itself has its attachment to the foot at this bearing surface on this blue plate. So I took out the, again, hydraulic cylinder, but I'm going to say piston. I took out this piston. It's connected to this blue plate. And we're going to see how we could add these controllers to it. As we're looking at this piston, I guess I should mention another of the conventions that makes sense. So this is in, let's put this into inches. So how long is this foot? It's 21 inches long, so that's a gigantic robot, but it's not hard to cut this size and just cut the size of everything. And it would be interesting to look at the robot. Some people might want a robot that big, but one of the things that we should look at is to go inside of this and see if we can measure. It's going to be a little bit. Let's just measure from here to there. So that's 2 inches in diameter, and this little blue piston is a little less than that, but the radius is 1. So pi r squared is pi times 1 squared, which is 3 basically. So it's 3 square inches. So if you had, say, 400 pounds per square inch as your hydraulic fluid pressure, this would be pushing down with 1,200 pounds of force. And this distance here is 3 inches. And this distance here is 9 inches. So it's 1/3, which means if this has 1,200 pounds of force, then it can push this by this piston going that way. It would lift up on this and put the robot where it's standing just on its toe, and it could push down with its toe at a force of 1/3 of 1,200 pounds, which is 400 pounds. So if the robot weighed 400 pounds, it could stand up on one toe just with 400 pounds per square inch. And the reason I mention this is that all of this material, I give it colors. Sometimes I change the opacity of the color so you can see through it to see what's going on. But the truth is, all of this material is simply going to be aircraft alloy aluminum, probably, except maybe tiny little places that need a lot of strength might be some of the alloy stainless steels. But it just seems to me like if I can put some colors in here, it helps to keep parts separate. And sometimes I change the opacity of the color itself. You can see the lines of this wooden floor are showing through this blue shaft and showing through the yellow head of this bearing. And the reason I made this opacity down is so I can show you the articulation features that would be placed inside of it. And the other thing I did with this is I just grabbed it with the scale feature and made it bigger. And I only made it bigger so you can see. And so these now, if you add these little articulation devices in there, these become articulated joints. And you can see that the articulation, the beginning point, the building block of the articulation devices, the body of it here with this little ball on the end. And the way you make a joint is this ball of this controller becomes superimposed, exactly superimposed over this ball of that controller. That's how it works. And the convention of the articulation program is once these two are joined together like that, you're not going to be able to do anything to get them apart unless you go in to edit the articulation. Because once you knock these apart or get them off index from each other, the joint begins to not function. So, for example, the articulation between this bearing that is on the lower leg and this piston includes that this blue structure and its bearings rotates around this point. So you take these articulation controls and you connect them together down here to this one, and then you stipulate that the only way that this articulation joint can work is a rotation where I suppose we can try it. So you specify that this is the only motion that's allowed is that. And I haven't grabbed it completely perfectly. That's hard. And I'm just trying to show you how this will work. But in the real program, the this little articulation controller would be exactly superimposed on that little articulation controller. And we would specify only that this joint can rotate. And so I brought it out to show it to you, because this shaft, piston shaft, has a sliding permission with respect to this cylinder. So this articulation and this one would not be an articulation of rotation. It would be an articulation of sliding, where this can go up and down this way. And the only motion permission that it has is for this to slide up and down inside of that. And so there is a visual or a three-dimensional structure demonstration of the articulation program. All right, and just to finish the point, the real structure will be made of metal, so it won't have variability of opacity. It's not going to be made out of glass or plastic or any kind of material that you can see through. It will be metal. And it won't have all these different colors to it, and it won't have this writing on it. None of that's going to be true. It's not going to have a red spring in there. All of that was done by me to make it easier to see. And what I wanted to do was the concept that these articulation controllers would be inside of the groups or the parts, and they would be in there like a bug that was living inside of something. And they wouldn't be all that visible, really, because they're not very big. But they're controlling how the object functions. And the important thing is there's going to be, I would like to make in SketchUp an option where you can make these controllers become bigger, where they would grow large enough that they would actually, this sphere would become a sphere that was outside of this group, so you could work with it and then you could shrink it back. And before we work through that concept, there's something about SketchUp and the way that SketchUp does scale that we have to look at. So we'll go to a different drawing. And in this drawing, we've created a sphere, okay? And I have the view set on so you can see through it. So there's the sphere that we created. Again, it seems to me that if you put a background on there, things are easier to understand. And I made these crosshairs and put them on this sphere and we can add hidden geometry, and you can see that these crosshairs are right at the midpoint of the diameter of this sphere. Okay, and I'm just showing how I made that. But when you get over into here, okay, one of the things you can do is take the view back so you can see through it. Okay, and then you can, let's turn off the hidden geometry, and let's take this and put it here. And we'll take this one and put it here. And we'll take a horizontal one and put it there. And you can see inside of this sphere is the geometric center of this sphere right there. And so I took this triangular pointed device for a purpose. And I moved this triangular pointed device so that it is got its little nose pointed directly at the geometric center of this sphere. So there it is. Okay, now we're inside the sphere. There's the geometric center of the sphere, and here is the tip of the point of this triangle. No big deal. So then we'll say, all right, well, this is a sphere that is inside of our group, and we would like to expand this sphere so that we can change our settings. And the way you expand a structure in SketchUp is you simply select the structure, hit the scale button, and you get any of these corners to try to increase it in a uniform way. And looking at it, I think I grabbed this one. But what happened was, when we increased the size of the sphere, you can see that the way SketchUp does, and I'm not complaining, it's just how they do it. I'm sure they have a reason. But in terms of an expansion, you can see that the center point of this sphere has been indexed off. The geometric spherical center of this sphere is no longer at the tip of this pyramid or this indicator place. And so we're going to make the suggestion to SketchUp, for the purpose of this articulation tool, that for these little structures, these spherical structures of the articulation tool, when you increase their size using the scale feature, they actually increase around the center of their geometric center, so that these lines defining their geometric center stay. So you have a uniform expansion of the device in all directions, and the geometric center of it stays where it was. And the other thing I'm going to suggest, just to show you, I have a feeling inside of this sphere, we probably, and I'll go back out to the view not being X-ray. Inside of it should be, I'm trying to make a structure that clearly says red axis, blue axis, green axis. So if you wanted to move this sphere around as a group, you could take the movement feature, and if you grab that corner where red, green, and blue come together, that corner is the geometric center of this sphere. Okay, and again, now we'll take the view back to looking through it. There it is in there. And I tried to make this so that it's, it's clearly obvious that this structure has 1, 2, 3, 4 points. And I'm trying to make a point where there's only one point is the point that we care about. And that point is the point that is the geometric center of this sphere. So remember all of that, because some of what I'm talking about with this articulation program with respect to expanding and shrinking the sphere using SketchUp, it's not going to work. And the reason why it won't work is because SketchUp does not expand things in that manner. But they could. I don't think it's hard. They just need to do it that way. And I think now we've got all our conventions put together. So we'll start talking about how to make this work. And the way I hope it's going to work is that first, I'll just describe some of how you create one of the articulation controllers, because there's a lot of variables and you need to understand what the variables are and how to assign them. Then we'll show how the controllers are put together, and then we will show how their motions can be specified to create the limitations that they add, or the limitations that they impose. We'll see. All right, so you go into Tools, and one of the tools will be named Articulations. And when you click on that, this will pop up. And you can either go to the main menu or you can show the pop-up. And the way I was thinking that this Articulations tool would work is there's a main menu that's got everything. But there's a pop-up that puts something down in one corner that has just a little bit of information that helps you to pay attention to your articulation tool and what it's doing. But it's not the whole thing, because the whole thing is going to be big enough that it will obscure your ability to look at your model. So you can add some instructions for the articulation tool, sort of conventions for how it works. So after you get to here, you can show pop-up, and then if you, and that really is, this is more like show pop-up configuration. This, if you choose this one, it goes to this one, and this one tells Sketchup whether you want the little pop-up tool to be floating or not. That's what yes means. And then where. And on the end of the green, here's my convention that I tend to use, is that red goes back and forth left to right. So, excuse me. Red is left to right. Left to right is red. Let's see if I can find, here it is. Red is left to right. Green is back and forth. Blue is up and down. Is that required? It's not required. It's just the way I do it. I tend to always make my drawings that way because a lot of the times you can hold down a axis control button, like the red axis button, and move things around. And it was nice if all of your drawings are the same way, because then you don't have to go find the axis and find out where everything is. So that's all that is. But if you choose to have your pop-up float at the drawing edge on the green axis, then it would go over here. If you have it float on the drawing edge at the red axis, it would go over here. And if you had it float on the drawing edge at the blue axis, it would be up there. That's all that is. And then if you're already, remember, whatever you've chosen as values for these are going to be that way. So if they're all pre-chosen and you're not messing with that, then you just don't mess with it, leave it alone. But you can also go to other more detailed portions of the articulation program. So you can change, alter, edit existing joints that you have already put together. Again, I've been calling it articulation because joint has sometimes negative but it is a joint. I mean, it's okay to call it a joint, just it's not a joint that has anything to do with drug use. Configure an existing joint, yes. Repair a broken joint. Go to the joint main definitions pane, or go to the label maker. So and you can see this little square here that says yes. It's not there, but this is just me making a mistake. I suppose I could fix it for you real quick. Not hard to. And we'll see if we can get that to go right there. And then we'll turn it red. And we'll get back out and we'll save it. So, okay. And the way I was thinking this convention would work in real SketchUp, if it was here and SketchUp created it, is you'd put your little arrow right there like that and click it. And when you clicked it, it would go to that. All right. So this is the joint or articulations main definitions page. This sort of tells you how you want your controller to work. And you're either creating a new joint or a new articulation, or an existing, you're editing. If you're going to edit one, you need to select it. So if you clicked on this, I assume it would display all of the different joints that you have. Each of your joints, you're going to give a name to it. So if you select it to edit, yes, you go over here, you know, there would be a screen like this that would pop up and you would pick the one you're going to edit. And I was, my thought on this is 4 or 5 minutes per section, and then we'll wrap it up and then I'll go to another one. And this is just part of building this video. I think when I'm done, I'm going to string all the videos together. So we're at the point where we have decided if we're going to create a new articulation or joint or we're going to edit one. And we're at the place where we're setting up our configuration, and there's what I call axis squares. I'm going to define these for you later. It has to do with setting up axes of rotation. And what you do is your controller is divided into numerical little squares. So this, for instance, is square 51. So on this controller, if you chose square 51 as your axis controller, then the rotation axis would be starting right there. And it would go from right there in to the geometric center of this structure, which is right there. So the number 51 axis of rotation would be that. That's all that means. And the plane of the axis of rotation would be the plane of this square. So that's if you chose square 51, your axis of rotation would be as drawn, and your plane of rotation would be as drawn. So that's what I mean by these axes of rotation. And 1 to 10 to 20 to 30. So I think there's 200 on this, if I remember correctly. And that's all. Oh, and there's one, of course, to let you select. This is to choose the polar axis that goes right down through the middle of it. All right. And the reason for doing that is it is my feeling with Sketchup, if you could select or specify these axes at an infinite level of density, it may overwhelm Sketchup. And if you had to specify it by typing in values, you're going to have to get into polar coordinates with bearing and right ascension, which is fundamentally confusing, I think, to anybody. It might not be confusing to astronomers, but all the rest of us would get mixed up. So if you wanted the axis to be sort of like that, you don't have to type in all these numbers and figure it out. It just turns out that that's 71. And there you go. It's all done for you. And all you're doing is specifying where is the beginning of the axis, where is the end of the axis, and what is the rotation plane of the axis. So we'll go back over here. And this controls the number of axis squares that are present on the end of the controller. That's what this means. This means that one of your axis squares will exist in a manner. Okay, so you can see here that this axis square. Okay, so if we went down inside of this device, here is the geometric center of this structure. Okay, so here is the green axis. And if we come back out of this thing, we can see that actually if you wanted to choose the green axis, you couldn't choose, looks like this is 91. You couldn't choose 90 or 89 or 100, let's see, 109 or 100. None of these would choose it because it's in the middle. It's in the middle of all of them. So there you go. And one way to solve that is to have this index these axes of rotation so that the red, green, and blue axis will go right through the center of one of the squares. I'm not sure if that's critical, but it might bother somebody that they can't pick it. So if you say yes to this, then it'll move those squares around so that one of the squares the green axis goes right through the middle of that square, and one of the squares, the red axis goes through a square. It's not, obviously not the same square, but there will be and since it's a sphere with a straight axis, it's actually going to be two of those squares, where the green axis goes through one and comes out through the other one. And that's all this does. A joint name, if you put the arrow here and click it, then it'll give you the opportunity to type in a name. And when this is the joint that you're creating between two controllers. And so this is the joint, this controller and that controller. And technically, actually, it's more that this is like that. These two are superimposed on each other, okay? That's the whole point of it, is that these two spheres are superimposed on each other. I did not show that because this I think is visually more understandable, but in the real situation, that's the whole point of the articulation, is that one controller that's controlling this group is linked to another controller that's controlling that group. And the way they're linked is between these two ends. So remember that. And this just gives you the opportunity to name. There's going to be two controllers. So controller one name, controller two name. It gives you a name for the end of the controller. Each controller has two ends, end one and end two. Again, I wish I could do this and make no mistakes, but invariably something happens. So at about 5 or 6 minutes, I'm going to save this and we'll restart. Okay, I've saved it, which is great. So if I get something wrong, I haven't ruined everything. Now, I've discovered, I like putting sometimes textures on a part, because if you increase or decrease the size of the part, the texture stays with it and you don't lose what part is what. And I've shown this down here as an example. So here is a controller named controller 2, and we'll go over here and okay, so here is well, we can choose this and let's just see what happens. So it's controller 2 blue 1. Probably that one. And it has this JPG file that I created. And you can look at these JPG files. I just made them in my graphics program. And you put a background color on it and you put some words in there. And the interesting thing about it is, if you pick it and you get your size right, then it's here on your structure. And you can have, here's end, because I think you're going to find with these, as you start adding them to your model, there's going to be enough of them that it's going to be easy to get mixed up as to saying to yourself, what exactly am I working on? So there it is. It's controller 2. This is end 1 of controller 2. Couldn't be more clear. And this is controller 1, and this is end 1 of controller 1 and end 2. And if you grabbed this with the Sketchup scale tool and changed the scale of it, because you can see that this is clearly bigger than that. And when you scale it up, it just scales up the label with it. So it's great. And you never get mixed. I mean, it's harder to get mixed up as to where you are. So as a favor to you, it is my opinion that we can request that instead of you creating all these JPG files yourself, let SketchUp do it for you. And so SketchUp will take these names that you gave and add that controller name to the body of the controller. So there. And it will take the, it will label N1 and N2. So when you're deep inside your drawing and messing around with stuff, you at least know where you are always. And that's important. Now, in all of these, finally, another thing is a control. Okay, here's controller 1, here's controller 2, and there's if these were moved together, you would see that end 1 of controller 1 is connected to end 2 of controller 2. So if we're going to push these together, controller 1, end 1 is connected to controller 2, end 2. So up here on this document, controller number 1, you have 2 ends, is connected to controller number 2. And in all of these SketchUp drawings, there's a bunch of different axes. There's the main axis, and then as you start going deeper and deeper inside of the parts and the subparts and the groups and the subgroups, they all have different axes. The axis of the joint would be the current selection, and I'm going to make it's just my feeling that you're going to be better off. You can see that I put inside of this that little triangular UFO at the geometric center of this sphere, with the red axis this way, green goes back the way, blue is up and down. And you may find that you stay happier if you just leave your controllers where the red axis is the one that goes up and down the controller, the blue axis goes up and down this way, and the green axis goes back, because it's easy to get mixed up. But it's your choice. You can pick whatever you want. But you do need to have the system to know which axis you want it to use. Now, I think there should be an articulations layer where you can put all these controllers in that layer, so that if you would like to look at your model and see what's going on, or render it, or whatever you're doing, and you just don't want all these controllers showing, you just turn that layer off. And I feel it should not, when you turn that layer off, it doesn't make the controllers stop doing their function. All it does is make them not visible. I feel like if you're going to have movement of parts of your drawing that's not under the control of the articulations, you are going to manage to goof it up so it won't work right. So if you want to have it moving around without the articulations controlling anything, you just need to get a new version of your drawing and take out the articulation. So I think you need to be careful if you have all these articulations and you've carefully put them in there so they work like they're supposed to. If you go disabling one of them, you may find that you regret that. It's an interesting concept. But I do believe they should be a point where you can, when you're creating all these articulations, SketchUp automatically for you puts them all in a layer called articulations, so that you can look at them if you want to, and you can get them out of your drawing, at least where where you can't see them and no one else can see them if you don't want to see them. And of course, yay, let's let SketchUp auto-populate all of this, of course. And you save what you did, or go back, so you're not so sure that you're confident about what you're doing, so you go back one page, or you save it and get out. All right, so we're getting there, step by step. All right, and we got through this page. We're going over to this page. This is the page that we use if we're going to change or reconfigure or edit a joint that we've already created. So you click on here, it gives you a list. You pick the one you want to work on. If you're looking at the page that controls everything, your overall handling system for this articulation program, you choose this one. Now, we had the thought with these controllers that we would think of them as though one of them was stationary and the other one was the one that moved. So we'll see how that goes. But that's the point is, you know, when you're talking about a motion, it frequently is a motion of one controller around the other controller. So we need to, if we configure an existing joint and we pick it, there's going to be two controllers, and this is where we check which controller we consider to be the stationary controller. So you can't click both of these, it's one or the other. This will be populated for you once you make your decision. Now, an important thing with these groups that you're going to assign a controller to is to get that controller properly placed into the group that you want it to control. And so we decided that we would put in this system that lets you have a very precise control of where you put the end of a controller. So you click yes, and it starts this precise positioning. Then you go to the place in the model where you want to put this controller end. Then you do Control plus click, and a crosshair will occur. You can pick that crosshair with your move tool, and you can move the crosshair to exactly where you want it to be in your group. And you do Control Shift and click, and the program will then take that end of the controller and place it where the crosshairs are. And so again, what you're moving around, the crosshairs are basically on that point right there. They are serving as that point. And when you do Control Shift and click, that point is placed on wherever you have put your crosshairs. And that gives you the ability to do precise positioning of your controller ball. Now, if you want, you know, again, one of these is still and the other one is moving. So if it's moving, you may want to specify what is the axis that it's moving around. And this is this opportunity that I gave you to pick your axis of motion using these squares. So you go over to the ball, you look around, and you back out of your program, you back out of your drawing, and you decide which of these axes is the one that you want it to be rotating around, and you touch that with your arrow here, this arrow, click it. Well, let me rephrase that. So let's say you picked one. Then you go over here and, you know, you pick the one that you chose. So if you picked number 90, then you would pick, let's see, right there's 90. So you pick 90. Now, if you wanted the axis of the rotation effect to simply be the red, the green, or the blue axis of your controller, which is that red, green, and blue axis that's showing there on the geometric center of that ball, you can just pick one of these. You don't have to do this, okay? Again, this option allows you in the pop-up to get a new axis for control without having to get all the way back into this page. And again, you are choosing what is the stationary controller and what is the one that can move. This is important, which is what is it that this controller is in control of? And if you want to change that, then it is this section of this page that lets you do that. All right, and we're getting to one of the central features of this articulation, which is figuring out what is it that the controller controls. And then we'll work on what does the controller allow it to do. And of the controllers in this, there's two controllers. One is the one we consider to be the stationary controller, and one is the one that we consider to be the moving controller. And if you, whichever one you pick, this is populated with what you have picked already for that controller. Now, if you haven't picked anything, nothing is here. But once you get this controller, whatever it is, controller 1, all settled, and you want to go and work on controller 2, you just go back up here and click this one. It takes everything that you did for this one and just saves it, and it lets you now work on this one. So that's how that works. This is saying that you would like to change or work on the objects and groups. This is the traditional SketchUp policy of putting a blue highlight around what you selected. Sometimes you need to look at what you're doing, and so you can have it not show that blue. And of course, if you click on that, the blue goes away. But if you go, if you click on do not show, it's gone. But if you click on show, it all comes back. You didn't remove any of your selections. You just took out that blue highlight. Now, you know, you're working along. It's a good day. Nothing is wrong. You've selected about 12 things, and the cat jumps in your lap and startles you, and you click something, and all the selections that you just made are gone. That's just a way that SketchUp works. You have to hold that shift key down, and you have to not get distracted. And I thought I would put an option in here with the clicking of selections, where if you pick this one, you can only add selections. So if you click it for no reason, nothing happens. If you click it on space, nothing happens. If you click it on an object that isn't selected, it will select it. But all you can do is add selections. And if you got it and you're like, I didn't mean to pick that one, you can come back to here and click. All that clicking does is deselect. So you click this one, you deselect your mistake, and you go back to this one, and all of the selections that you've made remain selected. That's nice, I think. And if you don't like that and don't want to do it, then just pick this one. You can ask it to behave like SketchUp always behaves, or you can ask it to only show you what you have selected. That way you can look at it and be sure you didn't miss something, particularly with complex drawings. And you can also ask it to show you what you have not yet selected, because you might have missed something. And you're like, I know I selected that, but you just didn't. So you can do this, and then hit this one, and it goes back to behaving like normal SketchUp. Now, there can be groups and subgroups, and you may have, I don't know, like the foot, which is a subgroup of the lower leg, and you're working on controls for parts of the foot. These are not really groups of the whole hip and the whole, you're working on the left ankle or left foot, and you're not even thinking about the right foot. So you can, if you want to, assign specific groups and subgroups to this controller link up, and it's not messing with the whole drawing. It's only messing with the groups that you have put into these selections. Now, sometimes you're in the position where you're done. You've got something you want it to control, and all the rest of it is the stationary part. So you can pick what you picked and hit this inverse, and all the other things you didn't pick get picked. Now, one thing that's nice about this system that I'm proposing is sometimes in SketchUp you need to back completely out of it and look around and think about it for a minute. And SketchUp has some complexity of not really letting you do that. If you get far out of what you were in, then you're out of it. But this would let you save everything you've done here, and it would put a little minimize, go back to the configure existing joint page. That would be in the pop-up. So you could choose this option here. Everything you've been doing here is still there, but this kind of disappears. And you can wander around inside the drawing and work on what you were thinking about. And once you got your mind straight about what you were doing, maybe you need to look at it from the front, look at it from the back. Then you can go to the pop-up and click on Unminimize this page, and this whole page comes back with all of these choices still there. Obviously, if you've finished with this, you can save it and go back. And if you've finished with messing around with the articulation program for this moment in time, you can save everything and get out of the editing portion of the articulation program. That's what this one does. And well, the way this would work is you'd get your little arrow and you'd put your arrow right here and you'd click it. Nothing happens when I do that because the program doesn't exist. But my thinking would be you'd put your arrow here and click it, and you'd be telling the program, please take everything I just did and save it and get me out of the editing of the articulation program. All right, so we have finished with this screen, which lets us create or really edit a joint that we've already worked on. I had some thinking about the question of naming things in SketchUp, and SketchUp doesn't add a name to anything. It crosses my mind that maybe SketchUp, whenever you make a group, by default, SketchUp will give the name to the group of the month, day, year, hours, minutes, seconds that you created that group. I don't know that anyone is going to create a group in less than a second. And all of the groups would then have a name, because sometimes this gets confusing when you're working in this stuff. You can't quite figure out where you are. One of the things that I thought would be nice is a naming convention where SketchUp gives you a bunch of labels and you can string them together to create a name. So for a human type or a robot that mimics a human, your list of labels could include like right and left, front and back, inner, outer, main, subsidiary, hip, knee, ankle, foot, medial, lateral, bearing, support, accessory. So you could go to a part in the ankle and name it the right ankle, inner, bearing, support. And on the other side, I suppose, would be the left ankle, inner, bearing, support. And you would just click on those labels and it would put them onto that group as the name of that group. I just thought that might be nice. And you can see here, this, I am just picking anything there. See, that's label 1. Maybe you could, when you invoked the articulation tool, there would be like an N right here for naming. And if you didn't click it, it would look like this. But if you clicked on that N, over here would be all the labels that you've added: right, left, forward, backward, accessory, main, inner, outer, bearing, bearing sleeve, or sleeve. See, in order to call it a bearing sleeve, you would just pick bearing and sleeve. And you could just click, click, click. And hopefully with 6 labels, that gives enough density of naming that you could name just about everything in your model where they were unique. And even if they weren't unique, SketchUp I have an option here in this that if you didn't pick enough labels, it would put a number. So if you picked main left ankle inner main bearing, and then you clicked another one like that, it would change the one you just named to left ankle inner main bearing number 1, left ankle inner main bearing number 2. It would just do it for you. And this is a suggestion that I was thinking, label maker. It's nice when you're messing around with these complex drawings that have a lot of parts, if all the parts have a name. And it's nice if they have names that are somehow related to what the thing is. And it's particularly nice if you don't have to sit there with your computer and have to type in all of these names. Because it's not that hard to just go click, 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 click. And there you have it. You're done. So this is the naming convention that I was considering to make as a suggestion to SketchUp, maybe inside of the articulation tool, or maybe something, maybe another, I don't know, a naming tool, or just something to consider so that you can quickly and easily name all these little parts inside of all of these bigger parts, subparts and main parts, or main groups and subgroups inside of subgroups, and they all have parts. So that was the naming convention that I was considering. I thought it might make sense to work through why I wanted to have the SketchUp program place the center of geometry of these controller ends for you. And I just wanted to demonstrate that that seems easy, but it usually isn't. Now, one of the interesting things I've noticed is it's kind of difficult to get SketchUp to place these squares if you don't have a guideline. I don't know why that's true, but it's true, for at least for me. And what I'm doing here is just making a display area. I've been surprised that it just seems easier to understand what's going on when you have something that you can look at. It helps to focus your eyes. So that's our little display area. And of course, I'm a great believer in saving. As you save along, that way if you manage to goof something up, you can always go back one. So we're doing 70, which had nothing in it. So now we'll save it as 71. And we're going to go get the structure that we want to put a controller on. So let's go see if we can find that. Frequently with what I do, it seems most of the time the highest version is the one that I like. So we'll go open that one and see what we find. Okay, and so inside of this, let's just pick something. Let's model, or let's add a controller to this indexing arm. This is the indexing arm that allows inversion and eversion, the piston that controls inversion and eversion, to stay properly indexed, even though you added dorsiflexion and plantar flexion. So we'll copy that, and then we'll go back to number 71 here. We don't need to save that, and we will get inside this group and paste it, and we'll take a look at it. So it's pretty small. Let's just take a look at, well, okay, that's millimeters. Let's convert this to inches. And let's take, and make that a little bit smaller. Put this over here and take a look at that. And once again, we'll see if we can get this down to a size that's appropriate for this structure. Okay, so there it is. And we have it floating in space inside of this containment. And now we're going to go get a controller, and we'll bring that into the same picture. And I believe, well, we'll save this, and then we'll go, I think it's this person. Here's one of our controllers. We'll get this green one. That's a kind of a pretty one. And we'll put it in here. So there it is. And if my memory is that this has inside of it the center of geometry. No, this one doesn't. All right, so I have discovered which one is the one that has the center of geometry inside of it. So we're going to copy that one and go back over here and paste that into place. And you can see that this is way too big, but that's not a crisis at this point. We can scale it. So we'll get it down to being about the size of what we're working on. And we'll get rid of this one because it doesn't help us. I'm just showing you that placing this controller is not nearly as simple as it might seem to you when you decide that you're going to do it yourself. So here's a controller. It's still a little bit big, but we can get back to that. The next thing we want to do is, obviously with this device, you're really going to want to put your controller going through the middle of it. Okay, so and you'll notice that it is currently lined up with the red, green, and blue axes because of SketchUp doing as a favor to you that when you import something, it imports it and adds it to the axes that you already have. And what is really going to happen in a real structure is it's going to be not properly oriented to your axes. So we might as well put that tilt in there. And we want to get this controller to go from this end to that end. And the question becomes, well, how do you find that? This is in the center of that circle, but we need it to be in the center of this. We can try turning on the hidden geometry. And there's a chance that SketchUp, as a favor to us, SketchUp will place for you an indicator that you're in the middle of this line. So we can take this face, which is on the green axis, and we can force it to be green and go down here till it's in the middle. And now we want to be sure we're not doing this. We want to do this to the group, because then we can erase this circle. So we'll make the circle a little bit bigger. And then we can take a copy of this line and put it and what that has done is indicated for us the place which is the absolute middle of this okay, so this little point right here is the middle of this, and we have to go down there and do the same thing on the other side. This is going to be the point where we put the center of geometry of that controller. And just want to be sure we don't have any residual of that, and we don't, so we're okay. So we can come down here now, presumably, if I did this correctly. Yeah, this is the same as that. So we could, if we wanted to, we can draw a line from here to here, because once again, Sketchup, as a matter of, as a friendly thing from Sketchup, it gives you the halfway point. So there's halfway. So we could, again, this is green, so we can make a green circle right here. Okay, and so we have successfully created for ourselves the marker points, and we can take the view back to not being X-ray. So these are the marker points. When you put your controller on there, one of the center of geometry of this sphere is going to be centered on that point. And the other center geometry of this sphere is going to be centered on that point. And this becomes a little bit easier to do. It's still, you can see it's a little big, but we're going to go ahead and just go down inside of here. And there it is. So that is the little UFO that floats inside of there. And we know that's the center of geometry of this sphere because we created it that way. So we can grab a hold of that. Now, so we're locked onto that. And we can go up here and get inside of this drawing and put the center of geometry into the center of this structure, and we can begin to see that this is just too big. Okay, it overpowers this, so we'll go ahead and shrink it to something that's more reasonable. And what you notice when you did that was, and this is the point that I was making, that center of geometry took off and disappeared. So we got to go find it again. And this is because of the way SketchUp works. And we're just going to ask SketchUp to give us as a favor that it shrinks around its center of geometry. So we grab that center of geometry again, and we're going out here to put it on that. Okay, so that worked so far. And the question then becomes, how are we going to get this up to there? And that's our next step. And again, my memory is that the red axis of this structure is this long axis here, but we can prove to ourselves that that's true by editing it. Yeah, and there, see, the red axis of this structure goes here. And we might want to turn off the hidden geometry. So the way this works is we can, if we want to, make this a little bit longer this way. Oh, sorry, that's two groups. So we'll see. Yeah, we can pick this. We'll go back out and get this so you can see what's going on. Okay. This structure here, the axes of this structure are not quite what we want. And it's not that hard to change the axes. And it's frequently useful to get them away from the drawing. So now we should be able to move this in the red direction. Yeah, see how that goes like that? And see, notice by putting this in as a texture, it just keeps adding, which is wonderful. Okay, so now we'll take that out. We made that a little bit longer, and we're going to go over here to this end. And once again, the axis of this end is not quite right either. Okay, so again, we now have the red axis as being the axis of the long axis of this structure is the red axis. So we might be able to select that, and we should be able to go that way with it. There you go. And notice again, this is just traveling with us. So let's back ourselves, and you can always go like that and get all the way up out of the thing and get back to where we were. So here is this, and it's starting to look more like what we wanted it to look like, but because we moved everything around, once again, we got to go grab a hold of that indexing point and try to get it straight. So we'll go in here. There's the UFO in there. There's the geometric center of this sphere. So we'll grab a hold of that and we'll go in. Once again, this is now the third time that we've had to put it on that point. So now we have. But you may say to yourself, well, how are we going to get this up to that? Because if we grab this and move it around, it's going to move that. And this is the complexity that runs into you when you try to place one structure inside of another structure. And what you have to do is go in here to your rotation capabilities. So we're going to let the red axis be the long axis of this device. So the only other rotation options we have is rotating on the green axis or the blue axis. So we'll take the blue. Now remember, when we want to rotate around this center of geometry, and so that's a green it's hard to explain, but it's perpendicular to the blue axis, so it's considered green. So we can hold down the green axis and put this here. And then we come back out of here. And we can go all the way into here and grab the center of geometry of this structure right there. And then we can swing this up and line it up with that. So presumably this is now pointed at that, except that we have to go do the other axis, because I have a feeling, yeah, see, this has to go over that way. So that's the next thing that we have to do. So we'll go back down in here. And we did a green one, so it's not going to surprise me if our next axis of movement okay, that was green. I think that this is, well, it's just on that face. It doesn't really have any axis to it anymore because this thing has been tilted, but you can hold the shift key down and it forces it to have that orientation, which is what we want. And then we go over here, go back into this one, because this is what the point that we're trying to index it to. So we'll look for the little UFO inside of here and we put it right there. And then we go down this way. And we get back to our rotation axis, and we want to rotate it until it's rotated right to that point. And so it's my feeling that this is now pointed at that. And I think, if we're lucky, we can go to this. See, that's still red, and we can go to this sphere right here, okay? And we can take the sphere, and it's on the red axis, and we can start easing this up. And then we can look inside of here. If Sketchup will let me. There it is. See? There's the little UFO. Oh, it's right there. And again, for some reason, Sketchup is giving me the space cowboy problem where you can't see what you're trying to look at. And okay, there you can see what we're trying to do is get this point to go to that point. That ought to be doable. And we know that this is, we want it to travel along the red axis. So we should be able to touch that point and travel along the red axis to that point. And so now we have finally added this controller to this structure, even though this structure is not particularly oriented towards anything at all, really, in the drawing space. And I think that you can appreciate, oh my goodness, that was not simple. And that's why I wanted to set it up so that all you do is take this center of geometry and put it here, and take that center of geometry and put it there, and SketchUp does all that other stuff for you as a gift from SketchUp to us. All right, so we're going to talk about the controllers. We have set up what they look like, and we've set up how you give them a name, and we've set up that you can place them inside the model. And the next thing we're going to want to look at is what are they doing in there? And we have, again, this piece of that ankle and foot, and we've shown inside of it some of these controllers. So this controller and that controller are going to be controlling the angle that this piston rod makes with this blue plate. And technically, there probably should be a controller up here in this fashion. Now this controller is really connected to this leg. It's like a wall. It's a static structure, but it's the support point, because the angle between this controller and that controller is going to change, because as this dorsiflexion and plantar flexion blue plate moves, when this piston goes in, this part of the plate is going to be closer to there. And since this is closer to there, it means that this whole entire piston is going to rotate this way, which means that this piston is going to rotate with respect to this anchor point. So we really need to put one up there. And we'll go over and take a look at the listing out of what's present in the articulation tool. So we've talked about it all started with a smile, and it turned into something as big as this. We've gone through naming, and we're over really into this page. Now, basically, I did not put this sphere superimposed on that sphere because I think that's a little confusing, but they would be for real. And so this is controller 1. So the end 2 of controller 1 is going to be, the sphere is going to be exactly superimposed over the sphere of end 1 of controller 2. So each controller has end 1 and end 2, okay? And these spheres have inside of them, they have the geometric center of the sphere right there. So this point right here, the geometric center of this sphere, would become congruent with the geometric center of the other sphere, and they're linked together and they don't come apart. And I'm not showing them pushed together like this because I think it's confusing, but in the real situation they would be. And so now we have to say, what is it that these controllers do, in the sense of what they do is they tell the drawing what is allowed and what is not allowed. And it's basically a restrictive permission concept, in that the drawing can only do what they allow. If they don't allow it, the drawing can't do it. So this is the pop-up. It's a sort of a pop-up. I'm going to do a different discussion of a pop-up in a minute. This little pop-up, you know, if you chose the pop-up, that one, you would get this one. And this would show you what joint has currently been selected. And if you want to select a different one, you can go click on this and select a different one, okay? If you have a joint that you want to configure other things on the joint other than what is here, you can click on this and you can go configure that. One of the things we can do when we select a joint or an articulation and we're looking at the entire model, we might have some confusion as to where is this joint in this model. So this does this for you. If you click on this and go look at your model, you'll have an arrow that is pointing to the controller that you have just chosen. And this, by clicking on this, it gives this display system permission to show everything that is associated with that controller. And here are the various different rules. What we're trying to do is structure this so that unless you really meant to do it, it won't allow you to do something where you're like, oh, man, I didn't mean to do that. So this pushes you to say, what is it that you're doing? Okay. And of course, the controllers have two ends, and this is allowing you to move the controller around in the model. And again, once again, if you're going to move it around in the model, an option for you to pick is to use this precise positioning method. And I just went through why I think that's a better deal, because you can do it yourself. It's not hard. It's just complicated, and it takes a lot of time. All right. And we're getting into the specifics of how a controller can have an effect on what the model can do. And I want you to see, again, this could have whatever name you want to give it, but this one I've called controller 1, and it has two ends, end 1 and end 2. And what I want you to understand is that when this is all put together, there's really going to be, in any particular controller that you put together, there's going to be three spheres. One sphere is the free end of this controller. One sphere is where these two have been linked together. And the third sphere is the free end of that controller. So it struck me, controller 1, end 1. So it seemed reasonable that the free end of controller 1 would be end 1, and the free end of controller 2 would be end 2. But you can put this together any way you want to. You need to understand that there's three different spheres, and the sphere in the middle is really two spheres that are superimposed on each other. I hope that will make this make more sense. So controller 1, end 1, is the free end of controller 1. Controller 2, end 2, is the free end of controller 2. And the controller 1-2 articulation is the place where those two spheres, the other spheres, the not free end, it's where those two spheres are linked together. And so you can change the size of the sphere. If you want it to have a color, you can put a color to it. If you click on this, this means it shows the color. If you click on this, a color wheel will be displayed, and you can pick a color for it. You can show it, you can hide it. You can stipulate of this connection between two controllers and their spheres, what end is the end, or let me rephrase that, what sphere is the sphere that controls this articulation? Is it the end of controller 1, the free end? Is it the free end of controller 2? Or is it the place where the two spheres are connected together? And again, if we went back to the other drawing, which I think is this one, so you can see that this would be the free end of that controller, and this would be the free end of this controller, and this would be the place where this controller and this controller are linked together. It would make sense to me, for example, in this exact arrangement, that this would be the place that controls the angle. Although I would have to see, you'd have to have this for real to see what would happen. But my thinking would be that you would choose this to be the place that controls the angle, the angles that are allowed. Okay. Each controller set has 3 spheres, and we're back out, and what we're doing is we're trying to make this so that you have as much control of it as you can get, so it's your system. In addition to that, so you don't get confused. For one of the controllers in the group, it's clear that you would want to see, well, what is it that this controller is this side of the controller, what is it that it's controlling? You can show them only, you can hide them only, you can add a highlight, you can pick a color. Same thing for the other controller. And this will be a name here. This name would be filled in for you, populated by SketchUp, so you know where you are. Show it, hide it. And if you want to show both, you can click show here and show here. If you're trying to figure out what, 2 weeks have gone by and you can't quite remember what was I thinking, you can unshow all of this stuff and only show one of the, to look at it, to try to figure out what did I do. All right, so that's what that's all about. I do have the concept of a controller that is a slider type controller or a swing arm controller. And again, I want to go back out into the other drawing. Okay, this would be a swing arm controller because this is swinging around. It's a rotation controller rotating around this place where these two controllers come together. That's a rotation controller. This is a rotation controller because this hydraulic cylinder, the angle of it changes with respect to this. But this controller here of this cylinder is a slider controller when it is a controller connected to this controller. Okay, because this does not rotate, it slides, it goes, so it's a translation motion, not a rotation motion. So when you have a translation motion, I'm calling it a slider, as opposed to a swing arm, which is a rotation motion. And one of the things that I can point out in this system is this controller is a swing arm. Well, this controller is part of a swing arm configuration when this controller is looked at with respect to that controller. But this same exact controller, this one, is part of a slider controller configuration when this controller is looked at with respect to that one. And it is my hope that one controller can be connected to 2 other controllers. I'm just hoping that. It could be from a math viewpoint that you can't do that, that you would actually have to put 2 controllers here superimposed on each other, and one of them is running the swing arm and the other one is running the slider. That may be required by math. I hope not. Okay. So that is the question here of whether you're configuring this as you're putting together this building, this controller for a joint, whether it's a slider controller or a swing arm controller. If it's a swing arm, you can take whatever position this whole setup is present at in the model right now and set that to whatever you want to set it to. You set it to 0 if you want. This is just an option that shows you which way of rotation is considered by the articulation program to be a positive rotation. That's just a floating positive that will be there somewhere. Again, this is all contained inside of a layer. So if you don't want that showing in your model for some other purpose, when you close that layer, that plus is going to go away. It's just there if you ask for it. This shows for the rotation controller what you construe to be the number of degrees allowed to be the start position, and this is the number of degrees for the stop position. So the entire range of the controller with respect to rotation will be all the way from the start position to the stop position. So that gives you the ability to specify what is it that this portion of the model can do. And if you ask the model to do something where it has moved more than the range of this specification, then a little sign will pop up and say, articulation tool prevents this motion. That's all. Now, in the same way, for example, a door moves on its hinges. So if you push a force normal to the door will move. But if you push a force on the door that is not exactly normal, it's sort of a force on the door, but some of your force is pushing the door in a direction that it won't go in. And some of your force is pushing the door to make it rotate on its hinges. And what will happen in that situation is the door will rotate on its hinges because some component of your force on the door is a component that allows or forces or calls for rotation. And I would like to set this up in the model the same way. So if you put a motion on this model, what Sketchup will do is take the portion of your motion that's allowed by the controller and let that happen. And all the rest of the portion of your motion that you're asking for, it just won't do it. And if you're somehow or another, if you went to the top of a door and pushed directly down on the top of the door, what would happen is nothing would happen because you're making a force at right angles to the rotation of the hinges. And so you would wind up, you can push down as much as you want, the door isn't going to move. And so in the same way in SketchUp, if you make a request for a motion that is a motion which is prohibited by the setup of your articulation, what will happen is nothing will happen. And of course, when it's a slider, this is rotation in degrees. The slider is a translation. And this means that it will use the units that you have chosen for your drawing, or you can choose whatever you want. Again, it lets you specify the current position as being whatever. It gives you this demonstration of plus or minus, and that's the start position and the stop position. And I probably, if we might consider, if we move this down a little bit, we can type in here we'll go over here so I can see what I said before. Why not? So once again, just exactly like we did with the rotation controller, this just has a little floating plus sign in there that tells you which way is considered a plus sliding motion. That might become important when you're deep inside the model and trying to figure out what's going on. Okay. And it's certainly true that you might get into this thing, into your model, and move something around and say, well, what I had set up, I don't like that anymore. I want something different. For example, you could move the model around and bring the model into a position on this particular set of parts and say, actually, this is what I would like to be equal to the 0 position. So you click on this and the position you're currently in becomes the 0 position. Or you may have moved it around and actually you don't like any of it and you want to get the joint or the articulation back to where you considered it to be at the 0 position. So not a new 0 position, but the old 0 position that you used to have. And whatever you did with the joint, you want to undo all that. So if you click this, the joint moves back, or the articulation moves back to the 0 position, and it takes all of its parts with it. Now, the axis square, when I'm talking about the axis square, I'm talking about these little axis squares. I've already gone over that a little bit. And we need to talk about human beings and the world and mechanical structures and the way in which human beings have exhibited or created or forced to exist the dominion of human beings over the mechanical world. And an easy way to think about that is a 300 or 400 or 500 pound door. And that door is on very nice roller bearing hinges. And so you can take your finger and push on that door and make it swing open and swing closed, because you are not holding the door 3/4 of an inch off the floor. You are not holding the door so it won't fall flat down completely. You are not holding the door so it doesn't get misaligned and off angle, because the hinges are doing all that. And what you've done is taken all of the motions of the door that are available and you have constrained so that none of them are available except for one motion. That is the motion of the door rotating around its hinges. And so you take a human beings can move a gram or two all the way up to 50 pounds. Now you have a human being in control of a 400 pound door. And that's how human beings do that. And so it's my finding, it's my intuition, most of the time with moving mechanical structures, everything is going to be constrained except for one axis, or one, with respect to the sliding type of connection, one axis of translation or one axis of rotation. And it's not going to be surprising to me if most of the time what's chosen is the red, the blue, or the green axis. But you can pick whatever axis of rotation you want to, except that I've divided it into 200 choices, because I think from a SketchUp viewpoint, if you had an unlimited number of different axes that you could define, it's going to get out of control quickly. And in addition to that, choosing axes in a spherical structure requires a type of thinking and a type of math that most human beings are not very familiar with. So we're just going to say this is good enough density for picking the axis that you want. And so you just pick this, you click on it, and if you picked on this one, which would be, let's see what this would be. This is 105, 106. So if you picked 107, then 107 would be turned red, and you would know that 107 is the place that determines the axis that you've chosen for the axis of rotation or the axis of translation for this joint. And again, here is some other options. I'm trying to give you as many options as we can. This tells you whatever axis is controlling the motion is shown. This also allows you where if you're inside the pop-up and the only thing you want to do is just change which axis is controlling, you can click on it and it'll change it. And you don't have to get deep inside of this thing and go through all of this. It's like a bypass. And there's some issues associated with the display of the pop-up, because the pop-up needs to be a little tiny structure, a little bit bigger structure, or a bigger structure. And I'm saying that we can show the minimized pop-up as a very much minimized pop-up as an icon, or maybe an icon and this controller. I'm going to get into that next. On the minimize pop-up, if you've been messing around, you got everything just the way you want it, you can right click on the minimize pop-up and it will say, okay, are you done? Is everything the way you want it? Yes or no? If it says save and exit and you say yes, it does it. If it also can say, well, all right, so you've changed your mind, you're not happy with any of this, and you don't want to have any of this that you just did have an effect, you can say this, undo and exit. When you have the little controller showing, it would be a circle or a square, and it can be perpendicular to the current view, or the red axis, blue axis, the green axis, or the current rotation sphere. It just controls how the rotation controller is displayed so that hopefully it's easy to see. And this is the final endpoint that says, yes, I'm done, I like what I did, do it. Or, no, I don't want you to do any of this, and just get me out of this. That's what that one is. So I guess we're close to some final thoughts here. So you go to the tools, there would be a word here called articulations. If you clicked on it, this would pop up. You can go to the main menu of articulations, or you could go to the pop-up. This is the pop-up. Now, the pop-up has an icon, and the purpose of this is to allow it to be there while you're working if you need it. And so if you didn't want this whole entire square showing up, you could put your arrow here like this and click it, and it would show the pop-up. I mean the icon, and the icon would be just a little circle that says articulations. And if you put your arrow on the icon and clicked it, it would go back to this. And down here, you can put an X in here that allows that to happen. If you don't have an X here, then it just stays as this. And this pop-up will float in your drawing, and it floats in your field of view in the drawing, and you can choose where it does that. And once you're in this pop-up, you can go to different more detailed places of the articulation program. Now, you can also have placed into this pop-up various different articulations and the values that are currently true for that articulation. So if you don't select, first of all, if you can take your X out of this box and it won't show any of these articulations. If you put your X in this box, it will show the articulations, but it will show the ones that you have selected. So you need to select which ones you want to do that, and that's what this box does. If you click on this, it gives you a list of articulations, and you can choose which ones you want to be in this pop-up. And if you choose an articulation to be in this pop-up, then it would show what is the name of the units, what is the minimum value, what is the actual value, and what is the maximum value. And if you click on these arrows, it changes the actual value, so that by clicking on these increase or decrease arrows, you change the units. And if it's at 1 degree and you hit the plus, it goes from 1 degree to 2 degrees. And it actually, when you start clicking on this, you define this articulation as being in charge of the model. So once you start changing these values for this particular joint, the values for all of the other joints will change accordingly under the rules that you have for how these joints work. So when it's just displaying them, it just shows you what the value is. But if you click on these and change what the actual value is, the others change. If you go out in the drawing and you take groups on the drawing and move them around inside the drawing, all of the values for these displayed articulations will change if you're out in the model changing things around. And as I'm thinking here, we might have to alter it to give a ability to change the density of the units when you change the value. So we could add a okay. And by adding that there, if you put an X here, these arrows would change it by 0.1 of the unit. And if you put 2 arrows here, it would change it by 0.01 of the unit. And if you had no arrows here, it would change it by the unit. So if you wanted to change it by degrees, you'd leave all these blank. Say if this was a rotary joint. If you wanted to change it by tenths of a degree, you would put an X here. And if you wanted to change it by hundredths of a degree, you'd put an X here and an X there. And so that allows you to get some density of control for your changing of these values for these joints. And so you could have this little pop-up down in the corner, change the joint around, and look at what it's doing to the whole model. There is one other thing that interests me. Once you have articulations that have defined values, numeric type values, and that is the question of whether you can make animations with what is available with these articulations. And the interesting thing about an articulation is you can have a grid of animation, because one of the issues of animation is to have an action and then another action occurs after that. So that is sequential. Let's say you have the value of an articulation or a joint, and it started at 2 degrees and it went to 9 degrees, and it did that in 3 seconds. So, and when you called that A, so you could have another joint in your model that changes its value, and you call that B. And you could put A as first and B as second, and so they are sequential. But you could have another one that you call, let's call it F. And you could, in a grid structure, you could have A here and B here, but you could have F directly under A. And what would happen when you ran the animation is not only would A occur, but F would also occur. And you could adjust the time interval of either A or F so they had the same time interval. And the effect of that would be is that whatever the action A was, the action F would also occur. And another thing you can add is the nature of time, because if you had a graph where it was the percent of your time interval that you had used up, and the other one was the percent of your value change that you had asked for. So let's just for fun say you have 10 degrees of change that's occurring in 10 seconds. And so if you put a 45-degree line here, then that would mean in 1 second it's changed by 1 degree, in 2 seconds it's changed by 2 degrees, in 3 seconds it's changed by 3 degrees, etc. But you could actually put a curve here where it changes from 1 degree to 7 degrees in the first 2 seconds, and then in the next 8 seconds it changes from 2 degrees to 10 degrees. So you could, as you define your segments, have an option there for defining the way that time flows. And another thing would be an option in a segment somewhere in there to call time as negative. So basically you could create a mirror where it went from 0 degrees to 10 degrees, and then it did the exact same thing except it went from 10 degrees to 0 degrees. It's very interesting because that allows all sorts of different types of people to make animations, because you can take your time and create these segments and put them together, and you can make them run concurrently or sequentially. And the only thing that would happen, I assume, is if you put this animation together and ran it, and you had what the military people call it a gimbal lock, where you're trying to get something to do 2 things at the same time that it can't do, then it would just stop. And Sketchup would say, you can't have your model move like this. You need to rethink your animation. But that would be interesting, and that would be fun. I think people might like creating animations, because this is a segmental method of creating animations where you don't get so confused. And in addition, with complex structures that have multiple parts, there's plenty of time where 2 or 3 different parts have to be moving at the same time. And currently in an animation setting with SketchUp, that's a little bit difficult to do. All right, well, we are now done.